We are jumping straight into Rebellious Student, reversing teacher signals for reasoning exploration with Self-Distilled RLVR, published by researchers at Microsoft Research and KAIST.
Right, and the core insight here is it's a complete inversion of how we handle credit assignment. Because post-training large language models using RLVR reinforcement learning with verifiable rewards, it suffers from this massive bottleneck.
Yeah, specifically when assigning credit to, individual reasoning steps, right?
Exactly. And the industry standard to fix that bottleneck is self-distillation. You have a teacher model guiding a student model. But this paper finds a pretty fatal flaw in that setup.
Because on successful rollouts, forcing the student to imitate the teacher actually suppresses the student's own independent reasoning.
Yes. So to solve it, they propose RLRT, which stands for RLVR, with reverse teacher. Instead of just pulling the student toward the teacher, RLRT actually reverses the signal on correct rollouts.
So it actively amplifies the exact tokens where the student disagreed with the teacher but still got the right answer.
Exactly. This rebellious exploration leads to huge gains on math benchmarks across Quinn 3 base and instruction-tuned models. It basically proves that true reasoning exploration comes from leaning into successful divergence, not just blind imitation.
Welcome to AI Paper Podcasts, the YouTube series for technical summaries of the latest AI and tech papers. If you are an ML engineer or an AI researcher looking to break the exploration bottleneck in RLVR, you are in the exact right place.
Yeah, because the premise of RLRT takes this really standard optimization practice and forces us to look at the mechanical assumptions we make. Standard self-distillation assumes the teacher's path is always the optimal path.
Which, makes sense on the surface, but let's contextualize why that breaks down for reasoning tasks.
Right, it's totally different for reasoning.
Think about a middle school math classroom. You're taking a test, facing this awful complex algebra problem, and instead of using the tedious multi-step method the teacher drilled into you.
Which is always the most boring way.
Always. You notice this geometric relationship instead. You use a highly unconventional, creative method, and boom, you arrive at the exact correct answer.
But then you get your test back, and the teacher docks your grade.
Exactly. Because you didn't show the specific steps outlined in the textbook. By forcing conformity to a predetermined path, the teacher actively penalizes your mathematical innovation.
And the paper frames this mechanically as the optimization ambiguity trap. In standard RLVR self-distillation, using a baseline like SDPO, for example.
Step-level DPO.
Right, step-level DPO. We have a single model acting as both the teacher and the student. And the difference between them is just information asymmetry. The teacher gets privileged context.
Wait, so the teacher sees the ground truth?
Okay, exactly. The teacher is conditioned on the correct rollout or the ground truth, while the student only sees the prompt. Now, on failed trajectories, that asymmetry is incredibly useful.
Because the student messed up.
Right. If the student model hallucinates or hits a logical dead end, the teacher has the optimal map, so it provides a corrective signal. Distillation transfers that corrective signal token by token to get the student back on track.
Makes total sense. But the ambiguity trap triggers on the trajectories that are already successful, right?
Yes. The student navigated the maze entirely on its own, used its own reasoning pathways, and got a reward of one.
So it solved it. But standard self-distillation applies the exact same corrective mechanism anyway.
It does. It takes the teacher's highly probable privileged path and just overwrites the student's valid choices. It enforces imitation at the exact moment it should be, reinforcing independent reasoning.
Wow, that's so counterproductive.
It really is. Now, previous research has actually tried to bypass this overwriting issue. Like there's the SRPO baseline.
Oh, self-rewarding preference optimization.
Yeah, SRPO. It tried a binary approach. Like if the rollout is wrong, apply self-distillation. If the rollout is right, just turn off self-distillation and use standard GRPO.
Just a simple on-off switch. But looking at the benchmark results in Table 1, that switch is clearly not enough.
No, it's actually worse. SRPO performs worse than full self-distillation on complex math benchmarks.
Because flipping between them creates, conflicting gradients, right?
Exactly. GRPO promotes general exploration while self-distillation promotes strict imitation. So you end up with a model being optimized to be a rigid conformist half the time.
And a random explorer the rest of the time.
Right. It just gets confused. The real insight of RLRT is recognizing that ignoring the student's unique reasoning, by falling back to standard GRPO, it leaves performance on the table.
So we need a way to actively isolate and reward that specific divergence.
Yes, a mathematically rigorous mechanism to do exactly that on successful paths.
Which sounds incredibly hard. A typical rollout for a math problem might be, what, thousands of tokens long?
Oh, easily thousands.
Yeah.
And most of that sequence is just formatting, repeating prompt constraints, or basic syntax. We have to filter out that noise to find the actual critical branch points.
So how do the researchers solve that?
They break information asymmetry into two distinct metrics. There's position-level asymmetry, denoted as d bar t, and token-level asymmetry, denoted as d bar t.
Okay, so d bar t and d hat. Let's start with d bar t. What is that?
D bar t is the KL divergence between the student and teacher distributions at a specific sequence position.
Meaning how different their probability distributions are at that exact moment.
Exactly. And the authors rely on a Bayesian view of the teacher here. They model the teacher as the policy conditioned on the event of a successful reward.
Okay, and to connect that KL divergence to actual outcomes, they bring in Pinsker's inequality.
Yeah, Pinsker's inequality is the theoretical bridge here. It bounds the total variation distance between two probability distributions based on their KL divergence.
Wait, break that down for me. What does that actually mean for the model?
It proves that if you have a high KL divergence at a specific token position between the teacher who knows the answer and the student who doesn't,
Then that specific position is really important.
massively important. That position has a disproportionately high impact on the final outcome. It mathematically isolates those critical forks in the road.
That is so clever, because for the vast majority of formatting tokens, the KL divergence is basically zero, right?
Right, the position is inert. It doesn't meaningfully change the probability of success.
Yeah.
But at those key branch points, d bar t just spikes.
Okay, so once a critical position is flagged by d bar t, the algorithm evaluates the token level asymmetry, the d hat.
Exactly. D hat is the log probability ratio between the student and the teacher. And the sign of d hat tells us everything about the model's behavior at that fork.
So a negative d hat means what?
A negative d hat means the teacher's probability for that token was higher than the student's. The paper's semantic analysis in Figure 3 calls these exploit tokens.
And looking at the vocabulary for those negative values, it's entirely verdict-oriented. It's words like conclude, final, valid, incorrect, thus.
Yeah, the teacher model has that privileged context of the final answer, so it's super confident. It just tries to rush the sequence to a conclusion.
Right, it wants to get to the end. So then a positive d hat is the opposite.
The exact opposite. The student's probability is higher than the teacher's. These are categorized as explore tokens. They mark self-driven reasoning and deliberation.
And the vocabulary completely shifts here. It's words like, wait, consider, another, alternatively.
It's literally the manifestation of an internal monologue.
That is wild. The model is literally pausing to verify its intermediate work or pivoting to a different path.
Yeah, it's pausing to think. And knowing that tokens with a d hat greater than 0 represent this deliberation, the challenge is...
How do you translate that into a policy update without breaking the model?
Exactly. You don't want to destabilize the whole architecture. So RLRT integrates this translation directly into the standard GRPO framework, the rollout generation, the trust region machinery that keeps the policy from drifting.
That all stays the same?
Right, stays intact. The modification happens entirely inside the token level credit assignment. RLRT calculates a per token reverse weight.
And the equation for that is the exponential of the sign of the advantage multiplied by d hat.
Yes. And breaking down those mechanics reveals how aggressively it reshapes the gradient. In standard GRPO, the advantage represents how much better a specific rollout performed compared to the average.
Okay, so if the advantage is positive, meaning it was a good rollout, and the student defied the teacher at a critical token, meaning d hat is also positive,
then the exponent becomes a positive value. The exponential function outputs a weight significantly larger than 1. It applies a massive mathematical multiplier specifically to the tokens where the model decided to output... Wait, let me reconsider.
Rather than defaulting to the teachers, therefore, the answer is...
Exactly. It artificially inflates the reward for successful rebellion. And conversely, if the advantage is negative indicating a poor rollout, the sign function flips, and that divergence is heavily suppressed.
Okay, but hold on. Actively rewarding a model for going against the teacher's high confidence path sounds like a recipe for hallucination.
Oh, for sure. That's the immediate worry.
Right, because if we amplify divergence just for the sake of divergence, won't the model just learn to generate bizarre, convoluted chains? Like, it'll figure out that rambling gets a higher reward than just being efficient.
The authors completely anticipated that risk of unbounded hallucination.
Yeah.
That's why the second component of the algorithm, the reward-gated update, is the linchpin.
The reward gate, how does that work?
Equation 7 specifies that this reverse teacher signal is only applied if the rollout is verifiably correct, meaning the environment reward equals 1.
So if the rollout fails, the RLRT mechanism is just
Bypassed entirely. The
Okay.
system just falls back to a standard GRPO update. The rebellion is strictly audited by the final objective.
To prove why that audit is necessary, the researchers did an ablation study, right, with a variant they called RLRT all.
Yeah, RLRT all was a disaster, actually. They removed the reward gate, applying the reverse exponential weight to failed rollouts, too.
So basically rewarding the student for disagreeing with the teacher no matter what happened.
Exactly.
Yeah.
And the results in Figure 9a show a catastrophic failure. By training step 40, the model experiences total collapse. The response lengths just explode past 10,000 tokens per prompt.
10,000 tokens, wow. And the actor entropy, the measure of randomness in the model's token selection, that grows unbounded too, doesn't it?
Unbounded. Without the reward gate, the trust region bounds just fail completely.
The model basically learns that rambling endlessly avoids the teacher's exploit tokens, so it maximizes its reward through sheer verbosity.
Yeah, verbosity instead of actual reasoning. It perfectly proves that valuable exploration requires diversity, but the diversity has to be rigorously anchored to successful outcomes.
Okay, so with the theory and the safety constraints in place, let's talk about the empirical results. Do we actually get better models?
We do. The researchers evaluated RLRT on Qwen 3, 4B, and 8B base models and an instruction-tuned 4B model. The benchmarks were exceptionally rigorous, too. AIM MAP 500, AMC 23, HMMT 26.
And the performance gains are massive. RLRT achieved an 18% average improvement on the 4B base model compared to baselines like GRPO and RLSD.
And the 8B base model showed a 12% average gain. Seeing these improvements on base models is especially noteworthy.
Because they haven't been constrained by the alignment taxes from supervised fine-tuning yet.
Precisely. RLRT is definitively lifting the baseline reasoning capabilities. But for me, the performance metrics just prove it works. The causal intervention experiment, the reflection injection, that proves the underlying mechanism.
Oh, the reflection injection. This is fascinating. They designed a test to see if the specific critical positions identified by that high DBART-KL divergence were actually the causal levers.
Right. They wanted to know if those specific tokens were controlling the outcome of the reasoning chain.
And the way they tested this, they interrupted the model mid-generation and literally injected the phrase, wait, let me reconsider directly into the rollout context.
It just hacked it right into the prompt stream. And they did this at 3 distinct locations. At the token with the highest KL divergence, at a completely random token, and at the token with the lowest KL divergence.
So what were the results on the untuned base model?
It establishes the baseline causality perfectly. When the reflection phrase is injected at the maximum KL critical position, the rate at which the model flips from a wrong reasoning path to a correct final answer doubles compared to the random injection.
Wow, it doubles. So that empirically validates that Pinsker's inequality actually isolated the critical branch points.
Exactly. But RLRT's impact becomes super obvious when you look at this same injection experiment over the course of training. Over 100 training steps, the RLRT updates systematically amplify this flip to right rate at the critical positions.
It pushes it above 40%.
Over 40%, yeah. While standard GRPO over those same 100 steps allows that recovery rate to just collapse back toward the random baseline.
Because standard RLVR spreads the credit assignment too thinly across the sequence. It just washes out the benefit of the reflective tokens.
Right. RLRT's exponential reweighting acts like a magnifying glass. It concentrates the gradient updates precisely on the moments of deliberation that alter the causal trajectory.
It's training the model not just to generate more tokens, but to deploy computational effort at the specific junctures where it matters most.
Exactly. And understanding how it concentrates that credit leads us to the question of distributional shift.
Right, because is the model just learning to better organize existing knowledge, or is this exponential weighting fundamentally altering the vocabulary's probability distribution?
The paper analyzes this using Jensen-Shannon divergence to compare the output distributions of the fine-tuned models against the original base model.
And what do methods like standard GRPO or DIVER show?
Well, methods like DIVER, which relies on sequence-level diversity, they produce relatively minor distributional shifts. They basically operate within the base model's existing preferences.
So they take the top K highly probable candidates and just subtly re-rank them.
Yeah, they refine existing pathways, but rarely construct completely new ones. The RLRT exponential multiplier, on the other hand, is a much more aggressive force.
The mathematical mechanics of RLRT actually pull tokens from the deep tail of the base model's distribution.
Yes. If the base model assigned a probability of less than 0.001 to a specific token, meaning it basically ignored it, but the student model samples it during a successful rollout, RLRT applies that massive positive exponent.
That forcefully drags a near-zero probability token out of the deep tail and heavily promotes it in the updated policy.
The data shows RLRT promotes these rare tokens to the top 1 prediction spot over 10 times more frequently than the baseline methods.
10 times. That's incredible. It physically reorganizes the candidate pool, totally bypassing the standard top K shuffling to surface genuinely novel behavioral patterns.
Synthesizing all of this, the ambiguity trap, isolating critical positions, the distributional shifts, this paper fundamentally redefines the utility of information asymmetry in reinforcement learning.
It really establishes that the divergence between a privileged teacher model and an unprivileged student model isn't just an error rate to be minimized.
No, not at all. When audited by a verifiable reward, that divergence serves as a highly precise map of where the student model is innovating beyond its training data.
By mechanically amplifying the exact tokens where the student succeeds by defying the teacher, RLRT proves self-distillation can be so much more.
It evolves from just a tool to compress a larger model's biases into a mechanism for systematically expanding reasoning capabilities.
Which means whether you are fine-tuning raw base models for math reasoning or pushing the boundaries of instruction-tuned models, enforcing strict teacher imitation imposes a mathematical ceiling on the policy's potential.
Absolutely. And looking at the whole trajectory of AI development, the industry is increasingly reliant on RLVR and advanced distillation to push toward artificial superintelligence.
Right.
But the findings in this paper suggest that the foundational concept of strict alignment to a teacher, whether that teacher's human expert data or a massive oracle model, it contains an inherent limitation.
Because if the optimization algorithms only reward a model for exploiting the known, highly probable paths that a teacher has already mapped out, the system will never possess the gradients necessary to discover novel mathematical proofs or generate new scientific paradigms.
Exactly. Innovation requires divergence from established norms. A system trained exclusively on imitation cannot transcend the capabilities of its teacher.
True superintelligence might require algorithms that don't just tolerate deviation, but actively engineer and mathematically reward successful rebellion against the established map of reality. Keep the mechanics of information asymmetry and reward gating in mind the next time you design an optimization function.